Thank you, and please welcome Jason Ho.
The Large Hadron Collider is the world's most complex and biggest machine ever built. It is a particle accelerator, which means that it basically smashes particles together at almost 300,000 kilometers per second. That's about equivalent to traveling around the world 7.5 times in 1 second. It lies underneath the borders of France and Switzerland in 27 kilometers worth of tunnels. Why do we need such large, powerful scientific instruments? We need them so that we can investigate nature at its smallest scales, down to 10 to the negative 18 meters. Now, that is small. That is 100 billion times smaller than a flu virus. But it's at these scales that we can see, or we can peer into the fundamental building blocks of the universe. Using machines like the Large Hadron Collider, there's many around the world, we've been able to develop very accurate mathematical theories that predict what goes on at such small distance scales. An important part of any scientific theory is that it not only explains the data that we see coming out of experiments, but it also has the power to predict things that we might not yet fully understand. One thing is just matter around us. We know that most of what we see is made up of molecules. We know that molecules can be broken down into smaller pieces called atoms. We've been successful in taking atoms and separating them into their constituents: protons, neutrons, and electrons. Now, we've been able to peer inside neutrons and protons and see that they themselves have a more fundamental structure. In fact, the most fundamental structure that we're aware of. Inside protons and neutrons are particles called quarks, and they're bound together by other particles called gluons. The complicated physics that is involved with quarks and gluons is explained by an equally complicated and very intimidating sounding theory called quantum chromodynamics. Now, like any good theory, quantum chromodynamics explains well what we see in experiments, but it also predicts particles that we've not yet identified or seen in any experiments, really. So the question is, and this is my research, is our theory pointing us towards new exotic forms of matter? Are these particles, do they actually exist? Or is there something incomplete about our theory? What we need to do is identify different properties of these particles so that we can go out in our experiments and point them in the right directions to see whether these particles show up. We have very sophisticated theories that predict very sophisticated results coming from these experiments, and time will tell how sophisticated our theory really is.